Good morning. So, we will continue with the heat calculation procedure for multi-component fuel. Considering LPG, which has several gaseous components like saturated and unsaturated hydrocarbons and isomers, etc. So, we have already seen the stoichiometric air requirement calculation for this mixture. Let us now take this and do the heat calculation. So, now the components are specified as volume fractions here, volume percentages. So, the volume fraction will translate to mole fraction directly. So, if we take the case of propane, propane is 13.31 percentage. So, that will be 0.1331 the mole fraction of the propane will be. So, now after calculating the mole fraction of each species, the molecular weight can be calculated as summation of mole fraction into molecular weight of each species, the product of this. The molecular weight comes out to be 54.2 as we have seen earlier. Similarly, we can calculate the standard enthalpy of formation of the fuel. What is that? That is nothing but the enthalpy of formation of each species. Please understand, this will be in kilojoule per mole into the mole fraction. So, when this is a simple weighted average, when there is a quantity which is based on per mole basis, then mole fraction is multiplied with that, and this is summed for all the species in the mixture. So, by doing so, I get the enthalpy of formation of LPG in kilojoule per mole. Now, I use the mass fractions. If the enthalpy of formation is in joule per kg, then I have to use mass fractions. So, that means if I have a quantity which is molar basis, then I use mole fractions in the summation, that is mole fraction of that into the enthalpy of formation of particular species in kilojoule per mole, and this product has to be summed for all the species. But if it is in kg basis, then I have to use mass fractions. So, that is the simple change you have to make when you get the mole fractions or mass fractions of the component. So, similarly, the quantity which is molar basis, we can make it mass basis by using the molecular weight. Okay, so for example, if the quantity is in kilojoule per kilomole, then dividing this by the molecular weight, I will get kilojoule per kg. Now, enthalpy formation is got on molar basis. Molecular weight is also got. So, by using this, we can now write the equation, global single step equation for LPG in air as C 3.77 H 8.98. So, this is the equivalent fuel. How it is got is just adding the considering 1 kilomole of the substance. For example, in this mixture, if you add the percentages, it will be 100. So, divide by 100, so that you will get 1 kilomole of this mixture. Okay, the percentage corresponding to the 1 kilomole. Now, add the C and H and put the numbers in this. So, C 3.77, H 8.98, obviously it will not be an integer. So, for this, balance this assuming complete combustion takes place. That means you will produce 3.77 moles of CO2 and 8.98 by 2, that is 4.49 moles of H2O per mole of the LPG. So, this is equal to LPG. So, by balancing the C, H and O, I get this value for the number of kilomoles of air required. Standard heat of reaction is nothing but the reactants enter at 298 and the products are formed and they are cooled to 298 Kelvin. So, and the standard heat of reaction is written as the enthalpy of products, that is nothing but the enthalpy of formation of CO2 and H2O, because enthalpy of formation of N2 is 0, minus the enthalpy of formation of LPG, which we have calculated before. So, this is the value. From this you can take. So, in this way you can see that the multi-component mixing rules are used to get the required properties, and by using the mixing rules I get the enthalpy formation and try to get the heat of reaction. We can also do individually, but this is a simplified method. So, for example, minus 90.3 kilojoule per mole was the enthalpy formation of LPG got from the mixing rule, and you may remember the other quantities here. So, finally you get that the standard heat of reaction is minus 2479.1 kilojoule per mole of LPG. Okay, the standard heat of formation calculated by mixing rule based upon the composition considered. If the composition changes, that will also change, that you have to understand. Now, per kilogram of LPG, just make it per kilomole by multiplying by 1000 and dividing by the molecular weight. So, you get the 45,740 kilojoule per kg of LPG. Similarly, heat of reaction per mole of O2 and per kg of O2 are calculated. You can see that it is 12.88 megajoule per kg of oxygen. So, in this way, multi-component mixtures which are got in fire scenarios can be, the heat released due to that can be obtained. Now, let us see how to calculate the enthalpy of formation of solid fuel. Solid fuel, by proximate analysis and ultimate analysis, we get the composition of volatiles, that is percentage of volatiles, fixed carbon, moisture, ash, etc. on mass basis. Similarly, the elemental composition C, H, O, N, S, etc. So, now we have already seen that a consolidated or a representative fuel in terms of C, X, H, Y, O, Z and N, P. We have also done this for the multi-component fuel earlier. So, this can be constituted and the values of X, Y, Z and P can be evaluated using the data from the proximate and ultimate analysis. For calculating the heat of reaction, you need enthalpy of formation of this fuel. For the multi-component mixture constituted by LPG, since individual components enthalpy of formation was known to us, we calculated the enthalpy of formation of LPG by using a mixing rule, sigma Xi HFI. But in order to calculate the enthalpy of formation of volatiles, I need the composition of volatiles. As I told before, volatiles are several species again, CH4, C2H2, C2H4, C2H6, CO, etc. But the precise percentages of these should be known to us. So, complete characterization of volatiles has to be done. If that is available, then you can use this information and again do the same procedure. See, for example, if the composition of these species are known as volumetric percentages, then I can calculate the mole fractions, and mole fraction into enthalpy formation of each species can be done. Specifically, I need the enthalpy formation of these species, which is known to us. So, from that the mixtures enthalpy formation can be calculated. For fixed carbon, enthalpy formation is 0 because it is graphite, correct, naturally occurring element. So, if this information is available, that is the composition of volatiles is available, then only the enthalpy formation can be found, or else we cannot determine the enthalpy formation of the solid fuel straight away. We can do one more thing. Straight away, if you calculate the heating value of the solid fuel, using any calorimetry, so bomb calorimeter, etc. Then the enthalpy of formation can be determined from that. Let's go back to the first law. Q dot equal to enthalpy of formation of the products minus enthalpy formation of the reactant. Now, this is the equivalent fuel. Based upon the equivalent fuel, I write the stoichiometric equation, and products are known, because you will see that the hydrogen and oxygen will, hydrogen and carbon will convert to H2O and CO2. So, by writing this, we don't know the enthalpy formation of the fuel, but the enthalpy of formation of the products are known. So, Q is, if Q is known, so what is Q? Q will be equal to HP minus HR. So, which is nothing but HP minus, in HR not only it is actually HF of fuel only. So, if Q dot is known, HP is always known to me, because we know what are the precise products, then HF fuel can be determined. So, that is one way to determine the enthalpy formation of a solid fuel. The other way is, as I told you, you go and measure the composition of the volatiles and use that information to get the enthalpy formation of the volatile. Then you know enthalpy formation of carbon is 0. So, get the enthalpy formation of the wood itself. Now, the next topic is flame temperature. See, first we have seen what is the amount of oxygen or air required for burning a fuel completely, at least the theoretical amount which is required. Then we have seen when a particular fuel burns, what will be the heat release. So, heat release, there are two things: standard heat, where the products are cooled to 298, reactants also enter at 298. So, that means I extract all the heat possible. Or if the products leave at a higher temperature, what will be the heat release? So, it's in the flow scenario, it is only the enthalpy change, enthalpy of the product minus enthalpy of the reactant. So, that is the second thing what we saw. And also we saw how to calculate this for the multi-component fuel and wood, etc. Now, another information what we need from fire is what will be the maximum temperature that can be got in a fire scenario. So, for that, basically we have to know some estimate of the flame temperature. So, flame temperature is an important parameter that affects the fire propagation. Okay, if the fire is initiated in a particular location of a room, it can propagate to other materials based upon how much heat it releases and how much temperature rise it causes. Correct, the temperature rise what it causes will be able to ignite the other materials. So, the fire propagation, ignition of the neighboring materials or commodities, etc., and the mass loss rate, because the flame temperature, if it is higher enough, then the flame heat feedback to the material will also be correspondingly higher. So, the mass loss rate also will be dependent on the flame temperature. Okay, now the flame temperature itself is affected by the heat loss to the surroundings. The surrounding, if there is no heat loss to the surrounding, then we get what is called the maximum temperature. Again, there is nothing called complete insulation, correct? So, there will be some heat loss always, but theoretically at least we can find what can be the maximum temperature that can be attained when there is a commodity which is burning, okay, or a fuel which is burning. So, the maximum temperature in a given space is attained if the heat loss from the space to the ambient or the surroundings is 0. So, take the first law statement, Q dot equal to enthalpy of the products minus enthalpy of the reactants. Now, when I say there is no heat loss, whatever heat is released due to the combustion which is kept within the furnace or the space itself, then Q dot equal to 0. So, in that case we can say that the enthalpy of the product will be equal to the enthalpy of the reactants. Okay, so now enthalpy of the reactant mixture can be calculated at a known temperature. Reactants enter at a particular temperature, say 290 Kelvin, or even fuel can enter at 290 Kelvin. The oxygen can enter at a slightly different temperature and so on. But you know the temperature of the reactants. Okay, now how to calculate the enthalpy of the product mixture? That is dependent on Tp. So now you know what is HR. If you calculate the value of Hp at a given temperature Tp, so that Hp will be equal to HR, then the Tp will be the maximum temperature that is attained when the space is adiabatic, that is Q dot equal to 0. So this temperature, that is the temperature at which the enthalpy of the products is equal to the enthalpy of the reactant, is called adiabatic flame temperature, which is the maximum temperature that can be attained in a given space when there is no heat loss and the heat released due to the combustion is going to heat up the products to the maximum temperature. Now, let us consider the calculation procedure for the adiabatic flame temperature. So, adiabatic flame temperature can be calculated with this condition that Hp is equal to Hr. Okay, now calculation of Hr is straightforward. So, consider a reaction, say methane itself, for example. Okay, now the reactant side, the temperature of the reactant is known to me. So, it is basically the enthalpy of the reactants. HR is nothing but the enthalpy of CH4 plus 2 times enthalpy of O2 plus 2 into 3.76 times enthalpy of N2 at whatever temperature. But if it is at 298 Kelvin, the enthalpy of reactant will be only the enthalpy of formation of CH4. So, often I know that. Now, take the products. Here it is straightforward because I am assuming complete combustion has taken place. Methane produces 1 kilomole of CO2, 2 kilomoles of H2O, and nitrogen is inert. So, no issue. And please understand that this composition is at the maximum temperature Tp. So, if you calculate Hp as, so first let us take a value of Tp, say 2000 Kelvin, something like that, and calculate the value of HCO2 at 2000, that is enthalpy of formation of CO2 plus delta HCO2 at 2000 plus 2 times HH2O, that is enthalpy of formation of H2O plus delta H2O at 2000 plus delta HN2 at 2000 into 2 into 3.76. So, that will be the enthalpy of products. So, if your temperature what you have guessed, that is 2000, is correct, then Hp will be equal to Hr, or you can adjust that to get the value. So, that is okay. Now, when you say the composition of the products are known to you, that means you are assuming that there is no dissociation of CO2 or H2O. So, in that scenario, the adiabatic flame temperature calculation still has some iterations to be done. Like for example, I have to assume temperature for the products, calculate Hp based upon the composition which you have fixed, then calculate Hp based upon that composition for the assumed temperature, equate it to Hr, and if the equation is fine, then no problem, then that is the adiabatic flame temperature. Now, what happens is the maximum product temperature can be varied. For example, if we assume 2000 or 2200 and we got this, when you try to measure it, so we have adiabatic chamber, put a thermocouple or any flame temperature measurement device and try to do the combustion there. Finally, what happens is you measure the temperature. But when you calculate this in this procedure by fixing these the products without considering any dissociation, you often over predict the temperature. Okay, so the main point here is to calculate the maximum product temperature, the exact proportions of the species, that is CO2, H2O, CO, H2O2, everything should be known to me. Constituting the product should be known. So it is not easy to consider that. So as a first trial, what I can do is complete combustion can be assumed. That's what I have now demonstrated here. Consider complete combustion. CO2 is formed, but it is intact, it is not going to dissociate. H2O is formed, again it is very stable, and so on. Now I can find the temperature by balancing the HR equal to HP statement and considering some temperature. Okay, but as I told you, this value, what I get, say 2300 Kelvin, something like that I will get, that is less than or more than the value what I measure. Okay, so the theoretical calculation done without dissociation is often more than the value which I measure. So that means that dissociation of the products has to be considered to get some real values. Okay, in some cases dissociation need not be considered, where if you have excess oxygen, the flame temperature itself is reduced because the oxygen is in the products, and due to the absorption of the heat from this oxygen, extra nitrogen also comes in. No, when you have extra air, extra oxygen means you have to supply extra air, so extra nitrogen comes in. So nitrogen and oxygen, extra oxygen will take out some heat. So the flame temperature itself will be less than say 1800 Kelvin, etc. In such case, dissociation need not be considered. But in cases where the temperature can exceed 2000 Kelvin, CO2 will definitely dissociate. So dissociation has to be considered. Okay, so now the problem is what? First of all, I need to get the exact proportions of the species in the product mixture, and then I have to take into account of the dissociation of this CO2, H2, etc. Then I will get the realistic value of the adiabatic flame temperature. So what I can write here is the same equation, methane plus air, 2 times air gives say A times CO2 plus B times CO plus C times H2 plus D times H2O plus E times O2 plus 2 into 3.76 times into. I can also add several more species in this equation. So now if you do a calculation like this, then I can find the realistic temperature. Now problem with this is what? First of all, A, B, C, D, E, 5 unknowns are there, and the values of A, B, C, D, E depends on temperature itself. So if I say that the Tp is the product temperature, so it's assumed. Assume a value of Tp. Now then go to equilibrium. Chemical equilibrium. So what I do here, I consider CO2 giving CO plus half O2. Similarly, H2O giving H2 plus half O2. So two more equations I consider. So Kp1 and Kp2 will be the equilibrium constant for these two equations. Correct. This Kp1, Kp2 are calculated at Tp. Then I find A, B, C, D, E values. For the given Tp. Now find, this is first, this is second, and now find, because now the composition is fixed, now find Hp. Then fourth step is check if Hp is equal to Hr. If you are fortunate enough for the guess the value of Tp, if Hp is there, then fine. Composition is also got, temperature is also got. Now if not, if yes, stop. If no, repeat 1 to 4. So this means that this is the procedure for calculating the adiabatic flame temperature considering dissociation. So I will repeat again. So now in the previous slide, I have the equation where methane reacts with air, stoichiometric proportion, CO2 and H2O are formed and they are considered to be stable, no dissociation is got. Now here I will assume a temperature for the products, calculate Hp, compare it with Hr, if they are same then fine, or else iterate and get the value of Tp, which will be the adiabatic flame temperature. But often what I find is the adiabatic flame temperature calculated without dissociation is more than what is measured. So what is the procedure for considering dissociation? I put the equation like this, in which I have A times CO2, B times CO, C times H2, D times H2 and E times O2. I will get only C balance, H balance, O balance, giving 3 equations to me. So 2 more equations are required to complete. There are 5 unknowns A, B, C, D, E. From atom balance equations of C, H and O, I will get 3 equations. So 2 more equations have to be generated to go to equilibrium. So before going to equilibrium, first I have to first assume a temperature Tp and go to equilibrium and consider 2 equations for dissociation of CO2 and H2O and get the values of Kp1 and Kp2 at the value of Tp, at the temperature of Tp. Next, find the values of A, B, C, D, E by solving set of nonlinear equations, because 3 atom balance equations plus 2 nonlinear Kp equations will result. Solve this to get the A, B, C, D, E at the value of Tp. Now calculate Hp, because now the A, B, C, D is known, it is easy to calculate Hp and check whether Hp equal to Hr. If they are same, then no issue. That is the temperature for what you want, and what is the composition also is known. Parallelly, you will know both composition of the product as well as the temperature. If it is not, then you have to go back and re-guess your temperature. So basically, I will guess a temperature like say 1900 or 2100. If Hp is less than Hr in one case and Hp is greater than Hr in another case, then you can interpolate between these two temperatures and get. So basically some iteration is required, but this iteration, in each of these iteration I require to solve the chemical equilibrium. Okay, so in that way if you solve, I get a realistic adiabatic flame temperature. Okay, so the realistic value of adiabatic flame temperature is obtained by considering the dissociation of the equation products CO2 and H2O. Now I can also add several other products also, O, OH, H, etc. also I can add. But correspondingly more equilibrium equations, if you increase the number of unknowns, 5 unknowns, 2 more equations require. 7 unknowns, 4 more equations you require. That is 4 more elementary equations and chemical equilibrium should be solved for that. So the flame temperature calculated by the equilibrium approach is closer to the measured values. So that is the thing. So that means that, see, it is not easy to measure temperatures always. So if you have a procedure which can give you realistic temperature, that we can use, and thermodynamic calculations can be used to get those values, and that will be a typical maximum value which can be reached in a fire scenario. So Either you can develop your own code to do this, or you can use codes like NASA CEA to get the equilibrium flame temperature for several fuels and mixture of fuels. Now, let us consider an example now for solid carbon combustion. So, you have a char. Char means carbon plus ash. Let us say ash is not very high. So, predominantly it is solid carbon, and it is at initially a temperature of 298 Kelvin, and air is flowing through this char, and the amount of air supplied is 150% the theoretical value. Do you understand? So, C plus O2 giving CO2. Okay, I am saying that for one atom of carbon I require about 1 molecule of O2. Now it is 150% that. So, the equation is written here. Okay, now when I add 150% theoretical air, so now please see this 1.5 times O2 is of 3.76, it is 1.5 into 3.76 times N2. So, both in the product you will see that 0.5 moles of O2 plus 5.64 moles of N2 will be there. So, since you have so much of heat absorbing species in the products, your resultant temperature can be lower than 1900 Kelvin. So, the chance of dissociation of CO2 is small. Okay. So, the equation is C solid plus 1.5 times O2 plus 3.76 N2 giving CO2 plus 0.5 O2, the excess oxygen comes out, plus 5.76 N2. See, there are two things here. Since oxygen is there, nitrogen is also corresponding increase, that flame temperature is less. Whatever be the CO, that is also burned since excess oxygen is also present. So, in this typical scenario, the products are fixed, the composition products are fixed. So, we can straight away go for calculating the adiabatic flame temperature. So, I will illustrate the procedure. Now, air also comes in at 298 Kelvin. Products CO to 1 mole, 0.5 moles of O2 plus 5.64 moles of N2 leave at a temperature of Tp, which is the adiabatic flame temperature for me. What is the enthalpy of reactant? That is, for graphite, O2, N2 all are basic elements which are at 298 Kelvin. So, the enthalpy of reactant is 0 because HF of these three are 0, correct. So, HR will be equal to HC plus 1.5 times HF of O2, sorry, HF of C plus 1.5 into 3.76 into HF of N2, but you will see that all these three are 0 because basic elements. If, see, for example, there is a char bed and air at a higher temperature flows over this, say 500 Kelvin, something like that, then the enthalpy of reactant will not be equal to 0. You will see that for the air there will be a sensible enthalpy that you have to take into account. But in this case, since air also comes in at 298 Kelvin, enthalpy of reactant is 0. Now, enthalpy of product is calculated as the enthalpy of formation of CO2 plus delta H of CO2 at Tp. As I told you, either you can use the CP data or the tables to pick up the value of delta H CO2 at whatever be the value of Tp you have guessed now. So, let us guess the value of say 1800 Kelvin and take this value and calculate this. Similarly, for O2, only sensible enthalpy will be there, 0.5 into sensible enthalpy of O2 calculated at 1800 Kelvin, for example. Similarly, for nitrogen. So, now you get the value of Hp. This will be equal to 0 because HR equal to 0.